ability of distinguishing two quantum states. We did that for pure states, and now this definition is supposed to generalize the situation to mixed states, so distinguishing two mixed states. And well, we did this prep work, and well, let me write what we're gonna prove first before reviewing this, I guess. Yes. So we discussed, right? So we discussed at least two sort of distance measure, even though some of them are not actual distance. Like the fidelity is actually not a distance. I didn't prove this, I guess, but I guess it's yeah. For some of the property is kind of obvious. But first of all, fidelity. What would be more like a distance would be the infidelity, right? It's like 1 minus fidelity, just because if the fidelity is 0, it means that the states are orthogonal, right? Since it's just an overlap of the state. If the fidelity is, on the other hand, if the fidelity is 1, then the two states are identical. But the distance, you need something opposite, right? For distance of the two things is supposed to be 0, right? So you would want something like the infidelity instead, rather to be something like a distance measure, like 1 minus the fidelity. Although that is also not really a distance, but we digress. The trace distance or the minimum error probability has, I guess, a more clear operational interpretation, right? And in particular, so here, given this definition, we are gonna prove that the trace distance is actually the difference between the probabilities maximized over a POVM element here. Yeah, so you can imagine that the POVM element E is something that you measure, and then you get different probabilities from rho and sigma, right? And this is something that you can use or gather statistics to distinguish between rho and sigma. Okay, but we had to do some kind of prep work because this is we are in the territory now where we have to work a lot more with matrices and like eigenvalues, eigenvector. Not like we didn't work on this before, but yeah, now this really linear algebra on steroids, like probably you are facing in homework right now. So this definition, this absolute value means the positive part when you do the polar decomposition, right? Because for an arbitrary matrix A, if you do a polar decomposition, you can write as a product of unitary on the left times positive matrix on the right, or the other way around, or unitary on the right and positive matrix on the left. And this is one of the positive matrix that you can construct, right? The other one is square root A of A dagger, of course. And so this is the meaning of this absolute value of matrices here. And yeah, since the difference rho minus sigma is Hermitian, so you can diagonalize them. And since, you know, taking, so now I have to take a function of a Hermitian matrix which I can do by taking the function in the eigenbasis instead, right? Taking function of the eigenvalues instead. And in this case, it's easy. We can separate the eigenvalue into positive and negative one. There could be zero eigenvalue as well, but they just disappear, right? And they're not in the support of rho minus sigma. So the absolute value is just this, right? And moreover, because of this identity, because the trace of density operators are always 1, right? You get that actually the sum of the positive eigenvalues and sum of the negative eigenvalues have the same magnitude. Actually, that's kind of nice. And here P plus and P minus, I just denote the projector onto the plus and minus eigenspace, which is the sum of, so like the projector would be something like this, but except just throwing away the eigenvalues here, right? Same with P minus here. Yeah, and so by all of this prep work, we can write the trace distance in terms of the eigenvalues alone. So either the positive one or negative one. Right? And you can see this 1/2 is nice because now I can just combine these two together. Okay, so let's prove the theorem here. Well, which side maybe I want to start from? Here, maybe let's maximize. Let's find upper bound on this guy. Well, but now we know that these, let's see. Yeah, now we know that I can write this guy in its eigenbasis. And if I do that, I will have the trace will just turn to the sandwich. I will just sandwich the E by the eigenbase, the eigenstate, eigenvectors of rho minus sigma, right? So I have two sum again. Yes. Do I need? Yeah, I can do this. And then this part is positive, this part is negative. And so a simple implication is that if I throw this term away, then I can get something bigger. Okay. So yeah, let's do this equality condition later. So this is Ej, and this is a POVM element, so its eigenvalue cannot exceed 1. And so I have another, well, now this will just be the sum of the positive eigenvalues, which is just the trace distance. So let's look at a little comment. Let's look at what these the condition for the equality, right? So this one, well, clearly, if yeah, this will be equal if it has no negative eigenvalues. So if, or rather, no, that's one way, right? Another way is that this POVM element is not in the support of the, has no support on the negative eigenvalues. you can do this. Or everything is 0. Right, and this will be an equal sign if E is just projector onto the positive eigenvalue, eigenspace. Right? So we have that. So the maximum probability is maximized over the POVM elements, like your choice of measurement. The difference between the maximum of this, the difference between the probabilities is quantified by the trace distance. And let me write here that actually if you generalize the situation last time for a pure state to mixed state, then this minimum error probability would be, I hope this 1/2 is correct, would be something like this. Yeah, I think it has to be there because it can be 1, I think, the trace distance. Right, if they're orthogonal. Right. So if rho and sigma are orthogonal, right, all the positive eigenspace would be the contribution of rho would just be all the positive eigenspace, and all the contribution of sigma would be the negative one. Can you? Is it clear? Right. So if support of rho is here and support of sigma is here, so like they're orthogonal, right? But in this here I have plus rho and minus sigma, so this will become a negative eigenspace. Right. And this is positive eigenspace. Right. Yeah. Well, actually, if that's the case, then oh yeah, the max is 1. Sorry. Now, yeah, I guess it's. I guess you can see it now. So, because of I take the absolute value, right? So both will become positive eigenspace. Right. And so the trace of the whole thing is just 2. And then you have 1/2 here. So max trace distance is 1. Then of course, if rho and sigma are the same, then you just trace of 0 with 0. Any questions so far?
So the inequality becomes equality when E equals P plus.
Yes, I think so. Yeah, it can be larger. Actually, so I think it can be. Yeah, it can be larger than P plus, but it should not overlap with the support of P minus. Maybe we should do this, but I don't know. Yeah. Although, of course, in practice, you wouldn't know like what the rho and sigma. Sometimes you wouldn't know what rho and sigma are, right? So you cannot choose the POVM that distinguish them. Okay, what's next? Okay. If everybody is okay, I'm gonna start erasing from the left. So let's look at special case. Special case says well, for pure state, okay, well, we have seen this before. This is supposed to be well, so if the state is psi 1 and psi 2, you can compute that this would just reduce to what the expression that show up before. And like square root minus square root 1 minus the fidelity. For qubit, this is just 1/2. Turns out just 1/2 the distance between the two block vectors. The final case is if you have commuting density operators. In this case, this would reduce to the classical distance, the total variation distance. So, yeah. 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 And this is the TVD of two probability distributions. Okay, a lot of these will be boring part where I just list properties of these distance would be probably sprinkle with some proof to keep you awake. Yeah, but we're not going to prove all the properties. You can just look up in textbooks. Let's see. Yeah, let's erase this later. So properties. Let's see. So it is invariant under unitary operations. So unitary invariant. I don't know, unitary or unitarily invariant. Right. That is if I rotate both density operators with the same unitary array, it is the same. And well, you can see this. By noting that, let's say, yes, so this would have eigen decomposition, and then you can rotate this guy. Yeah, so this would be the same, right? If you think of so on this side, I would just have the eigenvalue being the absolute value of lambda of the eigenvalue. Then I rotate the eigenbasis. Over here, this is if I rotate the eigenbasis first, and that would still be diagonal and then I take the absolute value, which would take the absolute value out of the eigenvalues. And so these two are the same. And so now if I put it into the trace, right, then I use the cyclic property of the trace, and then U dagger comes here and annihilate this U. Second, the trace distance is, as I mentioned, this is a true distance. So the property of distance, right? So this is positive with equality even only if these are the same, the rho and sigma are the same. It is symmetric. This is easy to see. The third one, the triangle inequality. This is something that we have to prove. Okay, let's see. So this would be if I have another density matrix. Let's call it tau. So this would be the triangle inequality. Okay, and we can prove this by noting that, well, this is the same as if I project this difference onto the plus eigenspace. And so I don't need the absolute value here anymore, right? Because I already projected onto eigenspace with all the positive eigenvalues. But now I can use linearity of the trace. Right? So basically, I can, add plus tau and minus tau here, and then just split the trace into two. Yeah, and then I have, yep. Right. Yeah, which is the lie above. Oh, it's just, yeah, just the, I don't know, the base physicist tricks. I just add something and then subtract it back. Right, so I mean, you do this a lot when you compute some identity involving commutator, right, like in quantum mechanics. Yeah, so I just write, rho minus tau plus tau minus sigma, and then I get that. Yeah. More properties. Now this is number 3. We already know that it's greater than 0 and it's also less than 1 as we discussed. Right. sorry. Uh, yeah, maybe you're wondering about this guy. And this, oh yeah, sorry, this is not exactly the line here. Yeah, because the projector of this is not on the plus eigenvalues of this difference here. And so that is the cause of this inequality, actually. Right. Yep, so I don't know. Yeah, so the third property here, we already kind of verbalize the proof, right? That if with equality, if or even only if these two are orthogonal, right? Property 4 is that this is so it's kind of the another statement of the theorem that we proved, that this is the max TVD of between two probability distribution maximizing over the PLVM. Yeah, so maximize over the measurements. Yeah, let's say how we prove this, right? So TVD is just 1/2 of P alpha minus Q alpha. And here we imagine that alpha is the probability of measurement outcome of like quantum measurement, right? So it's just trace of E alpha with the state. Right. So this is, let's see. Well, I can first write this sigma right. And if you take the trace of two positive operator against each other, you will get a positive number, right? Like trace rho of sigma. So conversely, if I take the trace of a negative operator and a positive operator, I will get a negative number, and so I can throw away this part. So let's see. Yeah, actually I forgot about this part. I want to just have the part where the difference of the probability is greater than 0. Let's see. Yeah, sorry about this. Oh, but because yeah, this whole thing because I forgot this. Right. Yes. Let's see if it's because of. Oh, I see. Then now I can split it into positive and negative part, uh, which let's see. And then both parts should be equal. I guess it's probably from the normalization of the probability. Oh, sorry. Let's see. So I have positive part and negative part, and if I sum over all of them, so let's see. So there be this sum, right? And then there will be this sum where this part is negative, but because of the absolute value, I will write them like this, right? So this is 1/2, 1/2. And are they equal? Well, they have to, if I sum to, let's see, sum both of them, I have to sum to 1. Yeah. Can anyone see this? Like why they have to be equal?
If
If you mark
both
around, yeah.
term are equal, then that mean without the absolute sign, then that term has to be 0, right? Without the absolute sign. Oh yeah,
Yeah,
right.
here.
Oh yeah, because sum of p alpha needs to be 1 and sum of q alpha needs
Yeah,
to be 1.
yeah. Yeah, that's where I was going as well. Probably I have to sit down and write it to see it.
So sum of p alpha minus q alpha over all alpha is 0, and then you split into two terms, and then you can
Ah,
move one to the other side.
right. Uh, yeah. Okay. Is it? So some of this, yeah. And then I can put like 1/2, maybe. Yeah. Oh God, I want to. So like that would be half of it, well, not half of it, there'll be, I can split into some with positive difference and negative difference, right? So this is, but then I split the sum into this difference is positive and this difference is negative. Right? Yeah, now if you look up Wikipedia on TVD, there'll be some picture that trying to explain this. There's like difference between the part where P is greater and part where Q is greater is supposed to be the same. Then they draw some area under, above, curve something. Okay, yeah, thank you. Yeah, now, yeah, I can finally write this, and and now, yeah, finally write this. Now I can move the sum inside here. And now the sum over the POVM elements here will be the will be precisely the projector onto the positive eigenspace. Sum here. Which is the not the TVD, the trace distance. Any questions on that?
Where did we do the maximization?
I think this is probably the P here. Oh yeah, thank you. Yeah, because this is not right, because originally this, whatever this projector is, may not cover all this subspace that P is greater than Q. Right. Yeah, thank you. And then I just list other properties before we go off to fidelity, but yeah, please feel free to ask anytime, right, if you have any questions.
When we say rho is perpendicular to sigma, what does it mean? Mathematically, trace of rho sigma equals zero.
Yeah, I think probably there are many ways. Trace would work too, and the commutator, not, no, yeah, commutator doesn't work. Yeah, I think it has to be trace. Yeah. Or equivalently, the support of them are orthogonal, orthogonal subspace. Now I have some property that I will list without proof. Marginalization. So if I take, let's see, yeah, let me write this first to see if you will see what it means. Maybe. So if I trace out a subsystem the right, the distance will always, well, will cannot increase under tracing out subsystem, and this makes sense because usually, yeah, I think it's even true for all quantum operation, which probably the next property is that there is no way to increase distinguishability in general. Because if there is a quantum operation that can increase distinguishability, right, you will always be able to distinguish states that are not orthogonal, right? Yeah, so this is some kind of like fundamental limit on information theoretic limit. Then this one that I just talked about would be this property 6. So under any quantum operation, the distance also decreases. Decreases or stay the same. It's just it cannot increase. And the last one is just convexity. God. Yeah. If I have some mixture of different density operator with different probabilities, this is less than the convex combination. Sorry, I have to have sigma here. Okay, and that would be about all about the trace distance for now. Right. Yeah, to summarize, these are properties of this trace distance, which is operationally meaningful as related to the probability of distinguishing two states that now can be arbitrary mixed states. Right. It is a true distance. It has nice property, right? Like it's invariant under unitary. So if you change, rotate your frame of reference, it's still the same. For example, yeah. And in general, you cannot. There's no quantum operation that would increase the distance. And we're gonna do the same. List the. Well, we're gonna define fidelity for mixed state first, which turns out to be much more complicated than the trace distance. Okay. So for pure state, right, the fidelity is just this. Well, now we can make a guess for mixed states. But the chances that whatever guess that we come up with is probably not the correct definition, well, the definition people use. Maybe you want to do this? Well, it doesn't work because if I put in rho square, then this is not always 1, even though it's the same state. Yeah, not always 1, even if rho and sigma are identical. Well, probably maybe a lot of choice that you can make. Well, since the fidelity for if one of the state is mixed is probably something like this. So maybe you can, maybe you can split this and try to generalize to something like this. So what would this case be? Maybe I shouldn't spend too much time on this because it's going to be wrong anyway. And I don't know, maybe put the trace of row. I don't know, like trace of row, and then maybe I think of this as a trace of square root of sigma. So let's say it is square root of sigma, square root of sigma. Well, I guess I get the same thing. Yeah. So I don't know where I was going with this. But actually it turns out that the appropriate definition of the fidelity or the one that people accept for mixed state is this. And just hold your breath. Well, the first question when anyone sees this, right, is like, why the hell it is this form? Well, this one you can think of it as, maybe I need more space here.
That inequality should be less than or equal to 1.
Right, sorry. Yeah, thanks. So this guy, okay. And this turned out to be symmetric between sigma and rho, by the way, but it's not, probably not obvious. I can think of this, so let's see, this is rho, sigma rho. And then I can think of this as, oh sorry, yeah, that's fine. Okay. And if I think of this as, this as like the main matrix, this is nothing but the absolute value of this guy. So this is why is maybe just maybe we can start to see something. This is why this is a generalization of this kind of weird, strange classical distance between two probability distributions. But one of the usual justification for it is so-called Ullmann's theorem. I think there's two ends, yes. That the fidelity between two density matrices, that you get the same thing by taking a purification of the two density matrix, that I would write like this for now, and then purify over all the unitary freedom that give the, you know. Okay, so maybe let's unpack it a bit, step back and unpack it a bit, right? So if you remember about purification, right? So purification is if I have a density matrix, the purification is a pure state on a bigger Hilbert space that trace back to the same. If I trace out the ancillar Hilbert space, then I get back the same density matrix. Right? But there's a lot of freedom of you can, for example, you can apply any unitary on the ancillar system, and you will still the state that you will get will still be a purification of the same density matrix, because it's applying unitary on the other side on the other system doesn't change anything about your system, right? And this unitary freedom is expressed by the SJW theorem that we talked about earlier in the semester. We phrase it as a freedom of ensemble decomposition of the density operator, right? And so here I mean the purification of this matrix with some degree of freedom here, which sorry, they can be different. Yeah, they can be different. And if you maximize over, and this would be the pure state fidelity between the two purification, right? And Osman theorem said that if you maximize this is the same as the fidelity between the two mixed states. So let's say this is okay. You can do, for example, something like this, right? I mean, I guess this can be any part. You can do something like this, right? If you remember the tensor diagram, right, that this is the purification, because if I form the density operator and then trace back, then I will just join the wire here, right? And then the two copies of square root of rho will come together and combine to rho. Right. But so this is the case where, let's say this is case where this U is just identity. But in general, I can have I can apply any unitary to either side, right, or to both sides. But we learned that the ping pong property, right, that you did in the homework as well, that in particular for this spatial maximally entangled state, you can always move unitary on one part to the other. You just have to put the transpose on it. Right. So I'm gonna make them pile up onto, so this guy can be VUT or UVT. Right. And for the order here, you just imagine you just sliding this guy, right? So that U and V, and for the first one, for the first one, I would slide the U down here, and it's become U transpose. So I will define, so let's see. So just to fix the convention, so let's see this for example would be sigma v applying to the unnormalized state, for example. Okay, so now we can start proving this. Okay. So let's see max of uv of this is, and then I just write down the definition of the purification. Now I have, okay, and then u, so let's see, have to be u dagger row. Okay, just to make it clear what I'm acting on, so this is on the quantum system and the reference system. This is like reference system, right? Let's see. Oh, sorry. Yeah. I can write the this unnormalized maximally entangled state in some basis, right? Well, let's see. Do it. Yeah, BJJ. Well, but one of the systems, so on the second system, the reference system, there is no operator acting on it. Right? So you would just take the inner product between them. So I would have a sum of like jj over here, sum of k, like kk over here, right? But then this second bra and second ket on the reference system will come together and then create a Kronecker delta, right? So in the end, there will be only one sum, right? Which now you can see it's going to turn into a trace. So now I have this, this, and then j, and then don't forget this one, right? And then this is just the trace. Right? Now I can move this U dagger over here and then combine them into one unitary. So now what I have to maximize over now is just going to be just the product, right? So which I can write as maybe just to prevent confusion, just give it a new name, U prime for V U dagger. Right? Well, and now here we have to do a little exercise to see what this guy should be bounded by, or like how to maximize this guy, right? So, okay, maybe I should have used this part of the space. Maybe there's enough space here. Okay, so the thing that we are trying to think about, right, is something like this. If I have a matrix that's not necessarily Hermitian, right? And I have a unitary, what this could be or how could we maximize over this U, right? Well, so I can do, for example, the polar decomposition. So maybe I can write A like this. Right? And then I can move this V on the other side as well. Yes, for simplicity, I guess we can ignore the square, the power first. Okay. Well, so now what is nicer here is that since this is a positive operator, I can diagonalize it. Right. So it will have, if I do the eigen decomposition, right. And then here, let's say I combine it to like U prime again, just for simplicity. If I take the trace of here, right, so I do I need to write the trace explicitly? No, let's see. Yeah. So I do the eigen decomposition of this. And then the trace would just turn the outer product into an inner product. And so I would have J lambda J, Ej U prime, Ej. Now I'm looking at the time and we're gonna stop soon at this point. So maybe finish this and then I can talk about the rest of the properties on Thursday. Okay. Yeah, so this one, well, so we know that these are positive because there's positive operator. So if I take this out, well, not really taking this out, but right. So this. Right, so this would be the triangle inequality. And then this guy, since the modulus of the eigenvalues of the unitary operator is as most 1, right? So this is most 1, and so if I, so this would be the sum of the eigenvalues of the positive part here. And so what do we get here? Well, is that this, it at most a trace of basically the singular value of, basically the sum of the singular value of A. Okay, so now we can do this, right? So just use that identity. Which is maximizing over the unitary here. Okay. I would have, okay, the absolute value square disappear, or the absolute value disappear, and then I would have this that we want actually. Yeah. Yeah, and this is the fidelity between the two density matrices over there. No, I mean you have to switch rho and sigma over here, but yes, switching the rho and sigma over here would just be the same as switching it with A and A dagger, which has the same singular value. Right. Okay. So you can see why the fidelity is symmetric between the two arguments as well. Okay. Any questions? Because I think we don't have a lot of time left. We have like 4 minutes. And actually, we can say more about the form of this or how to write this. Write this in terms of, or write like find the maximum of u in terms of this matrix A. Okay. But we'll save that for later when we need to use it. Yeah, so that's the.
Sorry.
Mm.
Max of the max magnitude.
Mm-hmm.
What does it mean in the mathematical way? It means in the simple form or something like max of fx, something like that equal. I still don't understand about the meaning of these symbols in mathematics, about the infinite INF, MINMAX, and something SUP, I guess.
Yeah, I mean we're not using sup and inf here.
Yeah.
But yeah, just max, and I mean we can talk about the infimum and supremum if you want to, but we don't need it here.
Okay.
So max here just means that I can vary these two unitaries.
very ภาษาไทยเนี่ยคือ very ในที่นี้คือแบบว่าก็คือค่ามันเป็นอะไรก็ได้ใช่ไหมแต่ว่าเอาค่าแม็กซ์สุดของสองตัวนี้
คือค่าอันนี้มันเป็นฟังก์ชันของแมทริกซ์คือค่าของฟังก์ชันเป็นสเกลาร์แต่ว่าตัว argument เป็นแมทริกซ์
ก็คือ argument ข้างในใช่ไหมครับข้างในตัว
ใช่
ซึ่งแน่นอน
มันเหมือน x อ่ะ
ครับก็คือตัวแม็กก็คือมันก็จะเอาค่าแม็กซ์สุดในตัวเอาตัวเดียวใช่ไหมที่เป็นแม็กซ์สุด
สักตัวใช่ที่มันใช่ถูก
โอเคครับ
เนี่ยแต่ว่าแทนที่ x มันจะเป็นสเกลาร์เราก็แบบเลือกแมทริกซ์อะไรก็ได้แทนใช่ Yeah, so after this, we'll list properties of the fidelity as like what we did with the trace distance. Usually the properties will, like all the inequality will become opposite just because of the reason that I talk about that 1 minus fidelity should be like the distance instead. And then perhaps surprisingly, all of these properties of fidelity is usually is harder to prove than the trace distance. Yeah, by the way, yeah. So if you want to know all about distance as a Chris Fook PhD thesis from the 90s, which I link. I think I linked in the Git on the GitHub.